Alright, so today we're going to prove the following equality for solving the Gaussian integral, which you've probably seen before in statistics and other domains as the normal distribution, which has the bell-shaped curve. Try to solve the following indefinite integral. Pause the video and try to solve this integral and see how far you can get. But hopefully you try it and realize real soon that this is a non-elementary function, so you don't have a definite solution. But in the case of an improper integral that goes from minus infinity to plus infinity, it does have the integral does converge, and you get a pretty neat solution of the square root of pi. Now, in order to solve this integral, we are going to define it first as I would like to define a slightly more general integral that goes from minus infinity to plus infinity of minus a. I just, instead of a 1 here, I generalized it to, in case the coefficient is different than 1, but it's always positive. So in this case, I just have to note that a is greater than 0. I would like to rewrite the integral again, but in terms of another variable. This is the exact same integral. X and y are just our dummy variables, meaning that whether you use x to index your variable or y, it's just a name. The value of the integral will still converge to the same value regardless of the naming convention. And I just happen to name the value of the integral that we get to be I, and it's going to be a function of this parameter a that I just introduced for generality purposes. Now, instead of computing just I would like to compute I squared. And you would say, how would you compute the square of an integral? Well, if you just think of the integral as a number, because once you finish evaluating any integral, you will get a number, then it's just that number squared. So that number multiplied by itself. So it's going to be the integral from minus infinity to plus infinity over all the real numbers, minus ax squared dx, multiplied by the same integral, but this time I'm going to write it in red using our other dummy variable y. Now, since y and x are dummy variables, and in our case, when we are integrating this integral, x is the variable while y is a constant. So in essence, we can just let this integral here, move it inside the integrand without having any issues. We can rewrite the integral as follows. But now also notice that within this integral, y is the variable and x is a constant. We can let this exponential come here. All right, and also we can note that these are two exponentials, and we can use the power law to say that exponential of a times the exponential of b equals the exponential of a plus b. And so we get the integral from minus infinity to plus infinity for the x variable, and from minus infinity to plus infinity for the y variable, the exponential of minus ax squared minus ay squared dy dx. And we can also take the minus a as a common factor. And you might say now that instead of having one variable, you have two variables and two integrals to evaluate. It seems as though we are at a worse situation than the one we started with, which had one variable and one integral to worry about. So what's the deal here? Well, if we just examine the integral over the Cartesian coordinates x and y, in our case, x is going from minus infinity to plus infinity, and y is going also from minus infinity to plus infinity. So in essence, this integral is integrating over all space. So it's going over the entire coordinate grid. And we know from polar coordinates, if we remember our polar coordinates, so this is the x, this is the y, and suppose that you have a point in two-dimensional space, you can specify it by its y coordinate and its x coordinate, but there's also another way to look at things. You can say it's at a distance r from the origin and in a direction theta. And in our case, r will be, using the Pythagorean theorem, is x squared plus y squared. And if we look within our integral, this is exactly that. So we have r squared. So that's one thing. We can substitute for, replace x squared plus y squared by r squared. But we still have the dy dx to worry about. So how do we go from dy dx to dr d theta? We cannot simply say that dx dy should equal dr d theta. As a matter of fact, that is wrong. But what dx dy is equal to is r dr d theta. Found this proportionality term from the Jacobian matrix, which will be the topic of another video. But if we want to replace dx dy, then we'll put here r dr d theta. And then we have the boundaries of our integrals. Well, we know that the entire integral will take place over the entire coordinate grid. So in our case, it should also take the entire coordinate grid in polar coordinates. So the integral becomes integral from 0 to 2 pi. That is, we are integrating over all the possible directions. And from 0 to infinity, all the possible distances from the origin, meaning that in both cases, for both boundary conditions combined, they are equivalent to the Cartesian coordinates going from minus infinity to plus infinity in either direction, meaning that they cover all the points on the coordinate grid. And so the integral becomes exponential minus a r squared r dr d theta. Well, now this is a much simpler, well, one might ask, well, what's the difference now? We're sort of like in a similar position to what we started. We already started with an ax squared, and somehow here we have ar squared, but it's all thanks to this term that came from the Jacobian transformation. Now, our u substitution, if we take u is equal to r squared, then that means that du is equal to 2r dr. And if we want to take the limits, so if r tends to 0, u will also tend to 0. And if r tends to infinity, u will also tend to infinity from this relationship, and we can substitute it in here. So we get the square of our integral will equal to the integral from 0 to 2 pi, and we'll have our integral over u, which goes from 0 to infinity, the exponential of minus au. r dr from here, we can rewrite it as r dr is equal to du over 2. So we can substitute r dr for du over 2, and you still have the d theta intact. So we can solve this integral on the side. So 0 to infinity, exponential minus au du. But we remember that this is an improper integral and we have infinity. We should actually take the limit. Let's say as t tends to infinity of the integral from 0 to t exponential minus au du. And this will be a limit t tends to infinity the integral of an exponential is the same function divided by the value in front of the u, so it's going to be the over minus a from 0 to t. And so we have the limit as t tends to infinity of minus 1 over a 1 over e exponential a to the u from 0 to t equals the limit as t tends to infinity of minus 1 over a minus 1 over exponential 0. And as t tends to infinity, the exponential is going to blow up to infinity, so this will go to 0. And this is just 1. This is just 1, so the value to our integral will be 1 over a. That's the solution to this integral. And so our I squared will equal to integral from 0 to 2 pi 1 over a d theta, and remember that we had a half from this value, so 1 over 2a d theta, and this is just a constant. A is not a function of theta, so it can come out of the integral, and we integrate from 0 to 2 pi d theta, and now I squared is equal 1 over 2a theta evaluated at 0 and 2 pi, which is 1 over 2a 2 pi minus 0. So I squared is equal to pi over a. And in order to get I, we just take the square root on both sides, and we get I as a function of a is equal to the square root of pi over a. The square root of pi over a. And some people might say, well, it's plus or minus a, plus or minus the square root of pi over a, but that's really not the case. But because if you remember that the integral we were calculating represents the area under the curve under the Gaussian function, which is always going to be positive. So therefore we drop the negative solution to this equation, and we get IA equals the square root of pi over a. And in our case, the most popular result is square root of pi integral from minus infinity to plus infinity of exponential minus x squared dx will equal the square root of pi, because in this case a is equal to 1, and you substitute it in this equation and you get this elegant and neat results.